recording, and we're live. So before we get started on the actual contents of today's chapter, I quickly wanted to point something out to everyone, which is that, and I know a few of you have already looked at my blog posts for this kind of stuff. Now I've made a change to the blog posts, which is that for every blog post that I've written, which goes through the exercises in the book, I have also attached an HTML link to the slides that I've presented. So if you hit that link, it takes you to this kind of page, which shows you the slides I'm going to be talking about in just a second. Just so for, if you see yourself returning to this, or if other people are dealing with this, I thought, I'm quite proud of my presentations at times. So I thought, let's put them up there. So just so you know, this is up there now, and I've also fixed the issue where the blog post, which is centered in the middle of the page, and now it properly stretches to the edges.
Eric, just a quick question. So since you're posting your slides as a HTML file, are those HTML files? Like, do you use like a Sharingan or some similar software? Or?
Yes, they are. There's free websites. I use Convertico, which has a limit for PPTX, so PowerPoint file to HTML conversions per day per computer. But if you have access to 3 computers on 4 servers, you don't really care about the limit per computer.
How is it called?
It's called Convertico. Yeah, if you just Google PowerPoint to HTML, because with the newer Office versions, you can't save PowerPoints as HTMLs anymore, which I'm really sad they took that away from us. At least there's web pages who can do it for us.
All right, thank you.
Like you might also want to just like the small mini lectures you're giving with these slides, just cut those, like just cut the videos to only that part, and then put that on your website. You can just ask us whether we mind, being seen, because I don't, like, I am not that shy. So my face is welcome for the world.
That's a good point. I'll send out an email at the end of this seminar series, just asking for permission. If anyone doesn't want to be shared, then I just won't do it. But if I get a go-ahead from everyone, then I'll probably just put it up on my YouTube channel and link it here.
Yeah, because I think it's like the whole point is it's what you were struggling with after both reading the book and watching the lecture, right? That's most likely what other people are struggling with as well.
Oh, and there were struggles, and there will be again, which brings us over to what I'm going to talk about right now. And I just need to share the right screen for that one after I've gone into presenter view. So sharing that screen. There we go. So today, the second to last big theoretical chapter, at least, we are going to talk about measurement error and missing data. And in spirit of this, I decided to have a missing subtitle as well, because I just couldn't come up with a nice pun. So just going right into this and thinking of measurement error, where does measurement error come from? That's the first thing we have to be aware of when we do our analyses. And first thing that comes to mind is we could have measurement error in both sides of our model equations. We can have measurement error pertaining to our response variables and the values that we've measured for them, as well as our predictor variables and the values that we've measured for them. Now, the assumption that most models run with, not the ones we're going to build up to today, but all of the ones that we've dealt with so far, all go off of the assumption that the error in our measurements for responses and predictors is constant for absolutely each observation and group in the data. This is basically captured with that, in mathematical notation, epsilon at the end of a model, or mathematical formula for a model, if I get that correctly. Because usually the assumption is that that epsilon follows a normal distribution centered on 0. So it's symmetric and constant across the entire range.
Like, what about residual error? That's not part of measurement theory. That's like there's some variables that you're lacking, and therefore that bottoms out in like error and everything else.
Sorry, could you expand on that?
No, like let's say there's like your response variables is actually the sum of 4 things, but you only have 3 of them, right? Then like basically the last thing then kind of becomes the intercept, and like the error of the intercept is basically like because you don't know what that variable used to be, right? So you just have like that distribution is now your intercept, right? And you have two lacking. If you're lacking two errors, then like the sum of those two is your intercept, right? And
yes,
and maybe if those things that are unmeasured correlate with something, they'll actually also make the marginalized posteriors wider, right?
Yes, exactly. I think with what you're describing right now, we are moving into not even just missing data, but full on missing variables from the causal graph or DAG, which we draw, and might lead to unidentifiability of parameters. So like with the leg example, where our posteriors get so wide that we can't settle on any answer because now a few parameters have to do way too much lifting for the entire model.
But I was more going with the spirit of this measurement theory, where so it's like it's independent and all these things. So it doesn't measure.
Oh, sorry, Jan, we lost you there. Your microphone cut out. Or is that just me? Can you guys still hear Jan?
No.
Okay. No. Okay, Jan, while you figure that out, I will just march on because I'm going to be talking about measurement theory for a while, or measurement error, and we can come back to the residuals. But can you still hear us? Can you just nod if you can hear us? So I guess Jan can't hear us. I'm just going to pause the recording because I don't want Jan to miss anything. Or resume the recording.
I think he can hear us. Yeah, he made a sign.
Yeah.
Yes,
oh,
yes.
Cool. Yeah. All right. So we hope that Jan, you can figure this out over the next half an hour or so and then give us your feedback. But let's soldier on. So the assumption here is that the measurement error is always homogeneous across all of our data. But what if it actually isn't? What if there is heterogeneity in our measurement error? Well, in that case, most of our regular models will have biased estimates. And we need to, oh, Jesus Christ. I'm sorry, there's something weird going on with, sorry, 1 second. Now I'm having some troubles here. For some reason, my PowerPoint is insistent on showing me help files right now. Let's try that again. Okay, now it's working. Today is obviously just a day of bad behavior of technical equipment, I guess. All right, and we're back. So let's chat about an example of when we have measurement error in our response variable. We'll then chat about an example where we have measurement error in the predictor as well as the response. But for now, let's just stick to the response error. The example we're running with here is the divorce rate example that's come up time and time again throughout the study session or the study group sessions. The response here is the divorce rate. The predictors are age at marriage, marriage rate, and population size for our different states in the US, that is. And what we run into here is that we don't know the true divorce rate, D, but we do know the observed divorce rate. So what we're assuming here inherently with the model that we're trying to build to is that there are some observation or reporting errors in the census from which we get our divorce rate data. In terms of a DAG, so in trying to build up to a model like this, if in doubt, just draw a DAG. When we draw the DAG itself, we have the upper part of the DAG here, it's this triangle area, which we already know from previous examples on this. But now we add this measurement error part where the observation, the observed divorce rate, is a product both of the actual divorce rate as well as the population size in a state. So the more people are in a state, the more people will be there to get divorced. And the more actual divorces that are there, the more we will observe. We could also draw a graph from N to D, for example, or from N to M. again, there are many competing DAGs here, as there are quite often, but for now, we'll just run with the assumption of this DAG. And once we have a DAG, we can just let conditional probability give us the generative model for our Bayesian approach, where in this case, we know that the observation of divorce rate is normal distributed, and it follows a distribution around the true divorce rate for each state, and then some standard error, which we actually get from the data. That took me painfully long to get this when I was watching the lecture material by McElrich, because I totally missed that this here came from the data. And then I was wondering when we came to the model why there wasn't a prior specified for this. But of course, if it's data, we don't need a prior. We'll get to that when we get to it, and I'll point it out again. In mathematical notation, our model ends up looking like this, where now we have our observed model, our observed divorce rate that we are trying to understand. This follows a normal distribution that is centered on the true divorce rate, which we don't know, but we know that it itself, the true divorce rate, at least according to our DAG, follows a normal distribution centered on mu, with mu being a product of age at marriage and our marriage rate. So we simply just shifted what we're modeling from true divorce rate to observed divorce rate. That's all we've done here. So we just need to add some priors in this case, and we're good, basically. So we've added the prior for the true divorce rate, which we haven't observed, but which we want to estimate from the data, since we have the observed divorce rate with our underlying causal pathways in our DAG. And we also have the standard error of observation, which I didn't quite understand why there wasn't a prior for this here. And that's because it comes from the data. And so we don't need a prior for it. Now, it's debatable whether this is going to be applicable to the models we'll be running later on in life, because I could imagine that for quite a few variables, we may know that there is probably going to be measurement error, but we will not know the standard error of that observation, at least not directly from the data. We could guess it, and then we would have to treat this as a parameter with an associated prior. Just in this example, we do have the standard error observation in our data set. Once we code this up, just ends up looking like this, where I added some markup here again, where we have one D true, so that is the true divorce rate, which we don't know, but we want to get to through our observed divorce rate. And for each state in the data set, so that is that n in this case is just how many rows are in the data set. And so for each state, we identify one true divorce rate with this line right here in the model. And this is where I pointed out again, DSD, the standard deviation of divorce rate per, so observed divorce rate that is, per our state is actually already in the data set, and you don't need a prior for it in this example. So once we run this model, we get this kind of a result. And already we see some very familiar things here. First of all, here's our observed divorce rates, in this case for ME. Someone help me out. Which state is ME? I'm just stuck on Michigan, Mississippi, and Minnesota, and
Maybe
all those are
Missouri?
MI something.
Missouri?
Missouri?
Maybe. Oh,
some state with a higher divorce rate than average, as expected for the median age of marriage.
So maybe Mississippi, I guess.
But Mississippi doesn't have an E in it, does it?
Oh, let me check.
Yes, please do.
So Maine.
Maine? All right. Yeah. I
ME.
mean, the people in Maine drive like crazy. I can see that leading to some fights, which end in divorce, I guess.
I think so. That's what it looks like.
I mean,
yes.
it does make a lot of sense. It's a pretty tiny state, if I remember correctly.
Right.
Right.
Yeah. I mean, yeah.
Which could easily lead to us having some quite biased results in there, in comparison to the rest of the US. Now, This open circle here is the model true divorce rate, D true, which we get from our model. So we can see that this distance between the circled dots and the open circles now just gives us shrinkage. So again, everyone gets some shrinkage, as has been the theme of the last few chapters, I feel like, to make our estimates more robust and our predictions more precise. So what if we have an error in our predictor? That's the big question we're going to go into now. We've talked about what happens if we have a response. Basically, we just add a distributional assumption for our response and then just propagate the actual linear equation to a bit further down in our model. Now, that was a bit too much in one go. Again, we go with the divorce rate example. Everything's the same as it was before, but now we also don't know the true marriage rate, M, but we do know the observed marriage rate, M observation. And again, on the right-hand side, as you could see previously with the divorce rate observations, there is heterogeneous error across our spectrum. So clearly we need to account for the measurement error here. So how do we do that? Well, with the predictor error model here, you can see that still we're working with D observation and D true because we're still acknowledging that there is some error that is not homogeneous on our divorce rate data, which leads us to dealing with observed divorce rates instead of true divorce rates. And just to deal with our now added recognition of the measurement error for the marriage rate, we just again add some priors. So we just add a prior for our observed observation coming from a distribution which is underpinned by the true marriage rate, which we try to approximate and then feed into our actual regression model. And sorry, just admitting a few people who joined a bit late. And this will also lead us to rethinking the DAG, since we are now building a relatively complex model. And we can now realize that M and A, so marriage rate and age, are related in our DAG, as they are in real life as well. The older you get, the more people will be married just because they had more time to get married. So can't we use that information as a prior for our marriage rate? So can't we say that as people get older, the marriage rate will probably increase, and get that information into our modeling of observed, or into our, not modeling, but into our prior of the observed marriage rate? Well, yes, we can. Here's just the DAG to remind you of what's happening. This model that we're showing right now on screen is not optimal in this case, because it neglects that bit of information, and we could have a more certain estimate of our true marriage rates, given that we know there's a relation between age and marriage here. We could fix this by just putting the entire directed acyclic graph assumption into the model, but that would go a bit too far for just this quick overview here. So if you want to see how this is done, the chapter exercises have you covered. And we'll go into them later, obviously. That is if everyone feels up for it. So moving on to the results of this model. When we actually run this model, and I could have sworn I had a bit about the coding in here. I guess I didn't. So let's talk about the results of running this model. Again, we see our blue circles, we see our open circles, and basically what we get here is the observed divorce rate here with the observed marriage rate, and this right here is the modeled true divorce rate with the modeled true marriage rate. And all of these are pulled towards some central location, the population mean for both marriage rate and divorce rate. This leads us to having multidimensional shrinkage. So we just have more shrinkage and more shrinkage and more shrinkage in our models. In this case, this is shrinkage of marriage rate as well as divorce rate. In this case, we have a stronger shrinkage in divorce rates in comparison to marriage rate, because the divorce rate is stronger associated with age than is marriage rate. So more strongly associated with age then marriage rate is associated with age. And that's why this all gets clumped together a bit more in the divorce rates dimension. Does that make sense? Because I feel like I'm not using my words very well. Just a quick feedback. Serena and Roseanne, you're the only ones with your cameras on. Cool. Okay, I had a thumbs up. Ollie has a thumbs up as well. By the way, so happy to have you here, Ollie. I know your time is very limited. Really happy that you can join us.
Glad to be here. This is great.
All right, moving on. Now we talk about missing data. So now we graduate from measurement error and we just jump from the frying pan straight into the fire. I think that's how the saying goes, at least. So with missing data, most approaches, we all recognize that in certain systems and certain data sets, we just have to deal with missing data. I'm sure we've all run into these issues where we just don't have records for certain variables for certain observations, even though we do have records for all of the other variables. But just right there, a logger failed, some student or even ourselves didn't enter the data correctly, and so we just had to discard the data point because we couldn't get it back from the jobbled mess that we entered. Something happened. We don't have complete cases. Most models and most analyses only deal with missing data in the case that, or in the sense that they're just removing any incomplete cases. It's in R speak, is that NA omit function that is called in the data frame object, where you just get rid of every row that has an NA in it. And oh boy, it's hailing now. Welcome to me, I guess. In this case, we remove any incomplete case from the analysis, but that also means we discard a ton of information. Because if you just consider that there is a lot of information in all of the other variables. Let's say we're trying to build a super complex model, 9 variables, different interaction effects. But then for one of those variables, ever so often, we just miss observations. If we discard all of the cases where that is the case, then unfortunately, we will always be discarding 8 other perfectly fine values in the other variables, which could actually be really useful for our model. So alternatives to just discarding the missing data would be to replace missing data with the mean of the variables. So let's say we're having multiple sites which we're looking at, and for some of those, so basically our setup would be to try and model diversity at those plots all the way just located across all continents, and at some of those sites our temperature loggers fail. Now, one way to deal with this would be to simply just use the average temperature for all other plots and just assign the average temperature to all plots where we don't have temperature data. I think from this example it should already be obvious why that's a really bad idea, because there's no reason to assume that the missing data should be at the mean of our temperature data range. This would just bias all of our results towards the mean and potentially get rid of some really valuable information. Another way of dealing with this is multiple imputation, which is the frequentist counterpart to Bayesian imputation, which is what we're here for. So I'm not going to spend any time talking about multiple imputation. I'm just going to talk about Bayesian imputation over the next few slides. Basically, just to sum this whole thing up, missing data is, and I love this quote from the lecture, that's why I bring it up back here again, is grown-up measurement error, because it's the ultimate in measurement error. If your measurement error is so great that it leads to missing data, there you go. Now, the example that we're going to run with here in just a second is the body mass, milk energy, and neocortex brain portion example from back in chapter 5, if I remember correctly. But before we get into that, I actually wanted to build on one of the explanations in the book and the lecture, which didn't quite get as much detail in the lecture that I would have wanted for this, because I think this is a very intuitive example, even though McElrath had his doubts about it. So just to explain how data can go missing and what that means for our models, we should talk about the types of missingness or the types of missing data. And these are, just to quickly summarize, missing completely at random, MAR, missing completely at random is MCAR or MCAR, missing at random, which is MAR or MAR, and missing not at random, which is MNAR or NAR, I guess. Rolls off the tongue now. The example that we're going with here is dogs eating homework and how that influences the observed homework score following the true homework score, given that some student has some attribute, let's say how much they study, which influences how good the true score of the homework is. So in this tag, all the way to the left here, we can clearly see that the attribute of the student, let's say how much they study, influences the true score that their homework is worth. But the score that is finally assigned to the homework by the teacher will be influenced both by the true score that it is worth, but also by whether it has been eaten by the dog. And if it's been eaten by the dog, then it will be worth less, obviously. And this is the observed score for the homework. So if we run with this one and we just look at this graph over here, you can see right here, I already made that thing of S instead of A, because I was just so hell-bent on studying instead of attribute of the student. So the big question here is, when do we actually have a good approximation of studying leading to the observed homework score? Sorry, I'm not using my words well today. When is studying approximating observed homework score a good approximation also of studying affecting the true homework score? Well, if we look at the first case of missing completely at random, we can, in this case, just regress on A, so A on H star, because in this missing completely at random section, there are no backdoor paths which would add additional confounds between A and H star. So this is the best case we can have. If our data is missing completely at random, we don't run into any issues. Now, if our data is missing at random, and I think this is a bit weird, where something is missing at random as opposed to missing completely at random. When it's missing at random, some attributes of the student, in this case studying, influences, so the parameter which we want to know the effect on the true score of our homework in this case, which is A or studying in this case, also has a backdoor path that leads to the observed score itself. And in this case, we could make the case that students who study a lot neglect their dogs, and then the dogs are bored, and then they eat the homework. This could be a causal path that we're talking about here. In this case, we need to condition on something to close the backdoor path. And what we need to condition on in this case is, sorry, not A, it should be D. Now, if we deal with missing not at random, there is nothing we can do unless we know the mechanism behind the missingness process, which in this case is D. So in this case, while for missing completely at random, we have independency of H on D, given that we already condition on A. In the second one, we have conditional independence of H on D, so we need to condition on A. Sorry, I'm getting confused now myself, so if anyone wants to weigh in, please do. This all made sense to me when I wrote this up, but now I'm slightly getting lost again.
Yeah, does my microphone work?
Oh, it does. Welcome back.
Okay, thanks. So I would assume it's the other way around, that it's the middle one where you need to condition on A. But I'm also bad at DAX.
Let's try and walk through that, because we want to get to an understanding of how good A is. So the understanding of A leading into H star, and how good that approximates A leading to H, right?
Yeah.
So the true score H in dog eats any homework on the left-hand side. Let's just talk about missing completely at random for now. Is, yeah, because so H star in the DAG on the left-hand side is a collider.
Yeah.
Hence why we don't need to condition on D in that one.
Yeah, if we condition on D, then we confound, right?
Yes.
No. If we condition on H star, we
No,
confound. If condition on D is
yeah.
fine. We can do it or we can not, right? It doesn't matter.
Mm-hmm. Yeah, no, in this case, we're just good. Because H itself is just independent of D, full stop.
Yeah, student causes homework and some homework is eaten.
Yes, I think I've got these text boxes switched around.
Yeah, that's what I meant.
Yeah, yeah, because in this case right here in the center, note to self to fix this. Actually, let me make a note of this. Actually, you know what? We're all here. We can all just quickly deal with that, I hope.
So the way I interpret the other one is basically some students have dogs. It's random whether you have a dog or not, right? And then some students like they get homework and then if they have a dog, it might be eaten. If they do not have a dog, it does not get eaten. But it's not like the bad student has dogs and the good student does not have dogs, right? It's just like random whether you have a dog. So it is ignorable, but it is still like it is actually a confounder where when it's like the campus has dogs and therefore it's completely random whether it's eaten when you're handing it in, right? It's only an attribute of the homework itself.
Yeah. Yeah, that's exactly it. So now that we've switched the text boxes around, I hope now this makes sense to everyone else as well.
Yeah. Yes, like the way I see the first one is basically like it's the professor who has a dog and it eats some of the homework as he's grading it, and therefore it's not an attribute of the student that causes it, right? And in the second one, all of the students have some dogs, but it's completely random which one has dogs, so it is ignorable in that sense. But since of course like a subset, like a random subset of your data is going to be confounded by this missing this, it's going to be more variable than the first one, because it's like if you imagine you have like 10 times homework from one student, then that student might have 3 things eaten because he has a dog, right? And another student has nothing eaten. Where in the second one, it's like it's the teacher who eats. So like every student gets 1 piece of homework eaten during the course of the and then given A, I'm guessing that like then you what, like in the second one here, right? H and D are independent is what that fancy symbol means, right? Given A, yeah. So without A, I suck at DAX. So there's
A is a fork, and because A is a fork, there's a backdoor path that leads from D through A to H star all the way via H.
Yeah.
And that leads to our issue here. We need to close that backdoor path through A, and that's why we need to condition on A.
Yeah. It's fishy, right? Because A is what we want to condition on anyway, right? So that's why it's so confusing.
Yeah, it's already in the model. And that's why it's weird to say now we need to condition on A.
Yeah.
I think this will come into play much more when one deals with more complex DAGs.
Yeah.
But yeah, and on the right-hand side, as you already mentioned, there's just no way to take these apart because the dog is only focused on specific homeworks that will score a specific amount, higher or lower.
I'm guessing if you actually had, whether they had a dog or not, right? That could help you.
It could. If you also knew.
No, but it only needs bad homework. That's the evil part, right? So, and you don't have of course, if you have both access to if you have like the problem is of course that it's missing, right? If you had 8, then it's not an issue because you don't have 8, so you're screwed.
Yeah, but if you knew why or how dogs could prefer to eat certain homework depending on how much score it is worth, then you have a way out of the situation all the way on the right. But if you don't know the process that produces the missing data, then you're just stuck.
Yeah.
Mind you, you can still run models, but they might just have a really hard time understanding what's happening, and the imputation of missing data might be pretty shitty.
Yeah, but like if you know that it eats all the back homework, right? A good starting point would be, so it ate 30% of the homework. So the 30% worst homework must be there. So it's like a normal distribution with like the cumulative lower 30% being centered. And then you can actually get a pretty decent estimate of the mean, right? It's just you have extra variance on the lower part because it's centered.
Yeah, if you knew that, obviously, yeah. But if you don't,
if you know the process, you don't know the parameters of the process, right?
Yeah.
I think the middle one would be help. If you imagine there's between the A and the D, there's like a variable called like animal person. Like so there's an attribute of the student which is animal person, which causes them to have a dog or not have a dog, right? And obviously you could also close the gap by conditioning on whether they're an animal person. Right, but by conditioning on student itself, you also close the gap because it's just one step earlier, and that's the way the types works.
Yeah. All right. Moving on. Great to see that your microphone's back online, by the way. Let's talk about missing data in an example. So now we just had that hypothetical of what's happening with dog eats homework. Now let's talk about the example that I mentioned earlier, we'll come back to, which is the neocortex example back from chapter 5. The theory behind this example is that we have a response, which is the milk energy of different primates, so primate species, that is, and the predictors are average body mass and average brain size or neocortex percentage. So brain size identifying how much of the brain is neocortex. Suppose we're dealing, in this case, with missing at random. So the part in the middle that I just showed that was highlighted in orange, where I needed to fix something. So we already know we need to condition on something here. Neocortex percentage in this case is linked to mass. The heavier you are, the more neocortex percentage you might have. You might. This is just our assumption for now. Conceptually, what we want to do is, as you can see on the right-hand side, the actual data set, and you can see all of those missing values in the neocortex variable, we want to replace each missing value for our model with a parameter, which our model will then take as a task for itself to try and estimate the actual neocortex value for this one missing observation, each in turn. We can then obtain the posterior distribution for the missing values, which also, because now there's information flowing in several directions here, alter the slope of the regression estimate in comparison to just running with complete cases here. So just to point this out, before we get into the actual model here, we will first again talk through the DAGs like we just did with dog and homework, but now a bit less intuitive, I guess, to talk about all of the different types of missingness that we might encounter here, even though we will be dealing with missing at random. So moving forward, we have MCAR, we have MAR, and we have MNAR, missing completely at random, missing at random, and missing not at random. These are just the DAGs, and these are not all of the DAGs that could lead to these situations. These are just a select few, where MCAR, missing completely at random, we have some unobserved variable, which leads to variation in mass. Mass affects milk calorie percentage, that is, so mass affects calories of the milk. The unobserved variable also influences brain size, which then in turn affects milk calorie content. Terribly sorry, I am completely scatterbrained today and I don't know why. You can also see that through this unobserved variable U, M and B are linked. This is a fork. Hence why there is some information traveling between M and B. That's what we set out to know. However, this all gets exacerbated when we go to missing at random, and I'll point that out again in a second. There is some process here that leads to observations of brain size missing. In this case right here, that process is completely random. So just random observations have lost their brain size parameter, or sorry, not parameter, but values. And the observed brain sizes are simply just driven by the true brain sizes. and the process that leads to some of them missing. Now, when we go to missing at random, we can already see that missing completely at random would give us any problems because this process here is completely random and there's nothing that we can do to approximate that one. But if we move to missing at random, we actually do see in this one thought example that there is something at play here. And that is that the mass of the individual itself now also influences whether we have measured the neocortex or not. As for example, for particularly heavy species, let's go to the extreme and go to the gorilla. We might just not want to get close to them. Mind you, I do realize that measuring the neocortex percentage usually happens when they're already dead. So it might also be the other way around, that individuals with very tiny body mass have missing observations associated with them because no one wants to do the fiddly work of identifying the neocortex percentage for tiny brains. Maybe. And this would then lead to other observations missing. And here with the missing at random, we obviously need to condition on something, and we'll get to what we need to condition on here in a second. Now, when we look at MNAR, in this case, we have the issue of there is a process which we can't understand though, because it is, in this case, conditional on the underlying true data, which we try to get to from our observed data. And this is that if you have a big brain to begin with, maybe you just don't get observed. Or maybe if you have a big brain, because humans like to watch things that are similar to humans, you will be sampled much more accurately and your data will be preserved rather than if you're a tiny species. So if you've got a tiny brain, maybe the chances that data about you just hasn't been stored or has been lost is higher than if you have a big brain. These could be ways of how this comes to be. There could also be additional unmeasured variables here, all of which would lead to some issues. But let's talk about missing completely at random. So now I'll just walk you through all of these again separately. I had totally forgotten that I put these slides down, so I could have just gone into these straight away. So I'll just speed through them now. And if there are any issues with these, just let me know and we'll deal with them as they come up. So for data missing completely at random, that's the good case, right? There are missing data in our observed brain sizes, and the observed brain sizes are a product of the missingness process RB, as well as the true brain sizes B. There are no backdoors from B observation, which is what we have and what we try to use as an approximator of B true, or just B in this case, as it is predicting K, the milk energy content. In this case, K is unconditionally independent of RB, which means we don't have to account for that process. So we don't need to condition on RB. We have no need to impute anything here. But if we were to impute the true brain percentages, then we could add precision to our models, but we don't have to. So this is missing completely at random, where the missingness is fully random. Now, when we move to missing at random, we have this link right here. We have some missing data in our observations. This is a product, again, of RB and B, but now there's a backdoor path from B observation to K, which goes through B observation, through RB, through M into K, which means there is a confound in trying to use B observation to predict the effect of B onto K. So in this case, K is conditionally independent of RB when we condition on M, because then we close down this fork right here. So now our model needs to include M as well. So we must condition on M to remove the confound going from RB into K. Sorry, going from B obs via RB into K. In this case, we must impute the missing data to debias our estimates. This is missing at random, where we have this path right here that gives us our backdoor. And something is causing the missingness. It is not completely at random. And we want to deal with whatever is causing that missingness. Moving over to MNAR, again, missing data is in B observation. This is a product of the missingness process and B. In this case, again, we have backdoors from B observation leading to K. On the left-hand side, again, this is missing at random. Missingness is caused by a variable itself or by a latent variable, but this is the backdoor path that I wanted to get to. So from B observation into RB, over to B, and then into K, we have now a backdoor path, which would bias our estimates of trying to understand how B is influencing K when we only have B observation to use in our models. In this case, and I'm not going to walk through the latent example of the right-hand side, I hope it should be clear how that should always also be a backdoor path, because there's a fork in there with some unmeasured variable U2, and I went into it. With MCAR in this example, K is unconditionally dependent on RB, and there might be a way out of this. Right now there isn't, because we don't know the process that leads to data being missing dependent on B true. But if we knew how that process came to be from B, then we might be able to model RB and thus close the backdoor path if we could get a condition on RB. Unfortunately, in this case, we just can't. So this is where we deal with the missing data model. This is just what the model would look like in model specification terms, where right here, our B value is now just observed and unobserved values. So everywhere we have an observation, we have the actual observation value in our vector. Everywhere we have an A value, we now have a parameter in place, which the model should estimate for us, so that we then have an estimate of the true brain sizes or brain neocortex percentages for each of our individuals, or each of our species, sorry. Now, in this specification, this BI prior turns into a prior for the unobserved B values, but a likelihood for the observed B values, which the observed values are going to be compared against. So this prior gets updated with every bit of observed values to then also inform the unobserved values in their estimation through this being treated as a prior. This also is explained on the right-hand side as well. And once we just write this into a model, painfully easy because it's just another prior. That's all we have to do here. ULAM, thankfully, automatically detects NA values for us. But if we wanted to write the stand code itself, we would need to work a bit of magic here where we combine the NA values with the actual data, and Stan doesn't like NA values, so they have to be coded differently. In this case, a good example would be to code missing data values as -1, for example, because that's easy to detect in your Stan code. But alas, I digress. It's all in the exercises as well. Finally, once we run the model, we get some results. On the right-hand side, you can see the imputed values for our brain sizes, some of which make a lot of sense, others do not. So, for example, negative values for neocortex percent. I'm sorry, no, these are all standardized, so they actually do make sense. Because with standardized values, we can go into the negative space, obviously, of neocortex values. I got confused here because in the exercises, we were also supposed to run with this example, and I chose to not standardize neocortex sizes because I wanted them to be absolutely bound between 0 and 1. If we just look at the coefficients and the plot of the posterior samples on the left-hand side for the imputation model M15.3, and the model after incomplete case deletion, which is the base model, the no-no basically, we can see that our estimates with the imputation model are much more precise than the complete case model because there is more information here that we're making use of. As a matter of fact, as you can see, 12 values for B have been imputed. We have just kept information for all of the other variables for 12 records where we were just so happened to miss some neocortex percentage value. Which actually brings me to the end of my summary today. I could tell that I was not doing the best job of explaining this in comparison to the other times I've done this. I'm terribly sorry. I am weirdly scatterbrained today. But if there are comments or questions, I'd be more than happy to hear from you guys. That does not seem as though anyone has the need to communicate. Quick question, how's everyone feeling brain power wise? Do you want to go through the exercises now? Cool. Jan already raised his hand, Serena was nodding, let's do this. I will try to speed us through it because I can tell that I am just going out of energy. So I'll just try to make this relatively brief and take you guys over to this screen, share this screen right here. And there we go. So just going into this exercise by exercise, first exercise asked us to rewrite the oceanic tool model from chapter 11, which is summarized again here. And we were tasked to rewrite it such that we assume that there is measurement error on the log population sizes of each society. So if you don't remember this model, just speak up and we can go into it. Otherwise, I'll just quickly talk about how I got to the solution here, which is that in this case, all we really have to do is take our population variable, PI in this case, and simply just write another prior for this with a certain distribution for our true PI, which we don't know, but we know our observed PI, P star, so P star I, that is right here, which in my case just follows a normal distribution and some standard error around that. Mind you, P star I in this case is observed log population. So it fits with the log true population on the left-hand side. I changed this in the next exercise because it was a bit of a hassle to just carry on the log signs all the way. So next exercise will look a tiny bit different, although it uses the same model. And once we've got that, we simply just substitute our observed log population, P star I, in place of the true population size, PI, into our model right here. Voila. Now, instead of it saying log PI here, it just says P star I, and P star I is the mean of the distribution which the logarithm of the true population size follows. And suddenly we're accounting for potential measurement error in our population sizes. Does that make sense?
I'm a little bit confused. Okay, so there is not like so this is a thought thing, right? You don't have data, but we're assuming that there is measurement error, and the measurement error is what so we assume that that's the sigma p, right? That's some number. There's like a column of measurement error. That's the assumption.
In this case, this is why I think the lecture was a tiny bit confusing, because it assumed we knew the standard deviation. But in this case, we do not. And so I add a prior for sigma p.
Okay. Oh yes. So you're learning the distribution of P star, but it's okay. But it's not like you have like 5 Hawaiis, so you know the measurement error of Hawaii. So I'm like, you only have like one every island once, right? So how can you figure out what the measurement error? I'm like conceptually I'm confused.
This to me is Bayesian black magic. So I'm happy it works, but I also don't grasp the concept quite completely yet. All I know is that this works. But let's try and think it through.
Yeah, but I think the reason it works is like so sure you don't like if you had 5 Hawaii, you could actually say what is my measurement error of Hawaii, what's my measurement, like you could do it like island by island, right? But usually when you have only one of these things, you still have like you assume it has like some form like a line, and then you can you have a likelihood, which is like the displacement on the line, right? That's how your data goes through the model, right? And I'm assuming here you can say, well, like basically when stuff doesn't fit, it is because of this sigma p, right? It's like an over disbursement thingy. So if it sucks up here and it rocks down here, then probably we should move it around up here, right?
Yeah, I mean this all just leads us into shrinkage. This is just trying to to move our estimates as close as possible to the regression line
Yeah.
that we end on. And I think from that, I think the big disconnect that we're both suffering from is that when we think of measurement error, we think of measurement error for each different subset. So for Hawaii, for example, but what this measurement error actually refers to is the measurement error when pooled across our entire distribution of our population sizes for all of our different societies.
And it makes sense that there could be a tool on Hawaii we didn't discover, right? So there could be. Of course, like intuitively, all the measurement error would be in the same direction. Like those three tools we didn't find.
Yeah, you could also argue that with small populations, you might tend to be, okay, no, this actually leads into something else, but I want to finish that thought. With small populations, you could have highly accurate data, but this is where you would know the missingness process. So you could condition on population size, giving you measurement error. Sorry, not missingness, but measurement error. Whereas with large populations, you could be wildly off to the top or below of the true population size, but that's a different thing. That's not what we're looking at.
Your example is John lives alone on an island. He has 3 tools. We're pretty sure he has exactly 3 tools. On the entirety of Hawaii, we went out and like.
Sorry. No. This is not tools. The uncertainty here doesn't link to tools. The uncertainty here links to population.
Yeah. So we're pretty sure there's only one guy on John's island because it's 2 square meters.
Exactly. Yeah.
Yeah. Okay. Got it.
Cool. All right. I'll just move on. I'll just move on from here then. And Serena and Ruzan, please do step in as soon as something doesn't make sense anymore. This took me way longer than I care to admit to penetrate, and I still feel like it's just slipping out of my grasp. And if you guys feel like it actually, and I'll just put it out right now because now it's coming up. For the last session, which will be in 2 weeks, I would be super happy if you guys could prepare a few things. One would be, and I'll send out an email about this as well. One would be ahead of time, please send me things that you're still unclear of, and I'll try to see if we can find some nice ways of clearing those things up. And Jan, you might probably expect some messages from me going, yo, can you help me explaining this? And so there will be an interaction effect. They're just saying none. And also for the final session, I thought it might be pretty cute if everyone would just rock up with a 5 to 10 minute presentation of how they think they might solve something in the future with Bayes, or maybe even are attempting to do so right now, just so we can see what everyone gets out of this. But this is just in 2 weeks' time, and I'll send out an email about this probably later today.
About the last chapter or the whole general session?
In general, the entire thing. So one thing that I am still adamant that I want to understand better is reparameterization and how to get models to be non-centered, because that's just a black box to me. And if you have things like that, where if someone would ask you, what don't you understand about this? And your initial response is everything, then that's probably something that we should follow up on before we close down the study group. All right, moving on from there. Again, there's going to be an email about this, and participation in both of these, sending some extra questions and preparing a short presentation of what you want to do with Bayes going forward is completely voluntary. You don't have to do it. I'm still happy if you show up, but I think it would make for some nice conversation pieces towards the end of our study group if we had something to discuss. All right, moving on. Sorry,
I have
Jan,
one thing. I have one thing with regard to this missing value stuff. That is, I have a lot of things with regard to missing value things I don't understand. One of them is if you do a posterior predictive check, like usually if you don't have missing data, you draw a new fake data set. Like that's like, you know, you can correct me if I'm wrong here, but like the whole idea is you train a model, and like when you train the model, you learn the theta part of Bayes theorem, right? And you have like a posterior on that. And then you like, if you're smart, you integrate that out. If you're not smart, you just draw like a set of thetas, and then you actually draw data subsequently, and then you draw a new set of data, and you draw a new set of data, right? And then you get like a fake data set. So now you have a distribution over data instead of a distribution over data, which is like what like this generative model stuff is all about. Now, what trips me up here is now we have missing values. Since the missing value is now a data parameter in a sense, right? Do we if I did a posterior predictive check and like I had half missing, half not missing data, would I only draw the non-missing part, or would I draw like half distributions, half not distributions?
Can I just say, just fuck you for coming up with these super difficult to answer questions. But that's a tough one. So what I'd probably do for posterior predictive check would be to just plot it, and plot the regression line for the unobserved values or intervals as well. But only, so basically I'm thinking of plotting the regression line as the model sees it, plopping the observed data values onto the screen as we have them in the data set, and then just adding the predicted values from our posterior all the way across the plot, so that you can see that you can see in which location was I missing original data, and what does the model think now, how close is that to the regression line, and in cases where I have both observed data as well as what my model would predict now,
that
how close are they together?
That sounds more like you're saying, like if I'm plotting a line, you of course put the data on, and you put the distribution for the and that's fine, that makes perfect sense. I'm saying if you actually wanted to draw fake data from it, do you then draw, like, since the missing data is actually a parameter, is that not drawn then? I'm like, what does it actually mean to do a posterior predictive check when some of the data is actually a distribution?
I think once you, I mean, all that it should lead to would just be wider uncertainty intervals.
Yeah, but like, but yes, I agree. But like, maybe I'm misunderstanding something. I thought when you did a posterior predictive check, you actually drew a new fake data set, right? It's to get like like a long, what is the long running frequency of the fake data from my model. And now like there's this naive thing where when you have Bayes theorem, you have like the data, which is like the fixed stuff that is like these numbers, and then you have the stuff you don't know, which is all the parameters, right? And in missing value land, we have the data, which is the stuff that has these values. We have the model, and then we have like these annoying distributions of things that are missing. So it's something that is fit. So it's actually something that has posterior and lives over here in parameter land, but it's obviously data, right? Philosophically, it's data. So philosophically, like if you did a posterior prediction check and you should redraw all the data, you should also redraw all the missing stuff. Like if it was like a really amazing posterior prediction check, it would actually have new stuff missing when you drew it the second time, right? It would be different things that are missing the second time you draw it.
Yes, I agree with you there.
And I have like I'm just talking like very hypothetical, because I would have no idea how to actually do that. But like philosophically, like if one out of 10 data points were missing, and you're missing at random land, then it should be another one of those 10s that are missing the next time when you draw the fake data set.
Can you put that into an email with open questions?
Yeah.
Because I don't think we're going to be able to solve that right now.
No. Of course not. It's more like
but I want to. I want to get to the bottom of this.
Yeah.
But we definitely need some preparation for that.
Yeah.
Cool. No, absolutely. Thank you very much for bringing that up. I will stick with my initial reaction of fuck you though. All right. Let's move over to the easy question number 2. In this case, we were tasked to rewrite the model from above, but in this case, allowing for the imputation of log population. So now we have missing data on our log population, but the data that we do have still has some measurement error going with it. So basically combine measurement error and missing data. So in this case, all we have to do is just take the model from above. I'll just scroll up a tiny bit so we can see them both at the same time. And basically the big thing that changes, so let's go through this line by line. Outcome distribution stays the same. Linear model in here stays exactly the same. This is where the change now comes in. And this is where I just switched from log something something to just, you know what, P star now is just going to be log population here. And this is now where it gets interesting, because now we don't assume that P star I comes from a certain distribution of, well, we do know that it comes from a certain distribution, but the distribution itself has changed. Because now we're not looking at P star I following some true distribution. Now it just follows a, oh God, again, this made sense to me yesterday, but now I'm getting lost again. This just follows a mean distribution of all of our observed values with some measurement error around that. And the important thing to point out here is that with this specification, this distributional assumption right here of P star I coming from a normal distribution with some mean and some standard deviation is a likelihood for all of the cases for which we have data and a prior for all of the cases for which we do not have data, where the mean of P star gets updated with every data point that we do have data for, as well as sigma P getting updated with every data point that we do have data for, to then inform, to then come to a more informative prior. So basically this is one big adaptive prior for all of the unobserved data.
One thing I really like about this is, like, if you imagine, and this is like a general thing that is like really cool about Bayesian stuff and really cool about hierarchical model as well. Like, if you imagine you have this line, right, and you have one of them, so you have like everything else says it should be up here. It has a lot of tools, but like we don't know the population, right? Then like we know that probably it's a large island since it has a lot of tools, right? But we still put in the prior distribution on the population, right? But it's the part of it's the, like, if the distribution is here, right, and the line is here, then it's this upper part of the distribution which is congruent with the line, right? So when it flows to the likelihood of the outcome, which is where then it's most likely it's this part of the distribution, right? So even though we put in the whole distribution, it's not like we force the mean in and therefore we mess up. We put in the distribution, and since the distribution has some credible mass in the length where the line is, it will like heavily like shrink or whatever we call it up to that point. And like usually when we just put in the mean and cross our fingers, we can't do that.
Yes, it will at the same time also very likely pull the regression line that you just held up in the air down a bit.
Yeah. But most likely if the prior is broad, it will more be like, if let's say that like actually one standard deviation away from the prior is actually the like you can just say like if all of the data is within 2 standard deviations, right? Then of course like the top point is going to be only like if the very largest point is missing, then it's basically 2 standard deviations away, right?
Yeah.
Like more like hand waving math here, right? So it's not going to pull down because it's like the line is probably like the uncertainty of the line is usually small, and the uncertainty at that point is huge, and therefore like the line is pulled down very little and the point is pulled up a lot.
Yeah. All right. I think that covered that exercise. Again, just people stop me if I'm going too fast.
I have one other thought. This is like a half-formed thought, but it's more like if you go back to the monk example, where we hack the likelihood function because they're sometimes drunk and they're sometimes not drunk, right?
Yes.
In theory, that's actually worse than missing data, because it's like sure, we have like a process and we could explain it with the fear inflation, but like philosophically, like if we knew which day they were drunk, we would have a much easier time regressing it, because then we're actually inferring the probability they were drunk, right?
Yes.
And if we knew that 17% of the data is missing, we knew that they are drunk 17% of the time, and they just had the other 4% just happened to be zeros because they didn't do anything, right? That is like a really hard fit in that model. So actually, like that is a more difficult problem than the one we are dealing with now, where we have missing data, because there we have like there we have like a point inflation value, which is also congruent with not missing.
Totally agree. Yeah. As a take home from that, just tell your monks not to get drunk.
Yeah. But it's also like it's the crazy part is like, and I think like there's something wrong with our mind and like this dichotomy between data and parameters, right? Because like if in the monk example, like all of the zeros are data. It's the data of zero because either they were not, it was a big book that they didn't finish, or they were drunk, right? And now, like if we actually had more information, which meant we knew which day they were drunk, then suddenly they're like this missing. They're not their distribution instead, right? It's like having more information actually they become a prior instead of part of the likelihood, because in the other way we have two likelihoods, which is kind of counterintuitive.
Yeah, no, because in the other example we had the hierarchy of if this likelihood then this likelihood. But yes, if we knew when they were drunk, then we could just use that as a prior to telling us how much was produced.
Yeah, or we could just drop all the data points, like because like that this part of the model, the p one minus p or whatever the not drunk is. That's the thing, same as dropping all the missing values.
Yes, we would drop them if we wanted to get to an understanding of how productive they are when they actually work. But with the example that we were running with, we wanted to know how often are they drunk on average.
Yeah, but you just weigh it back by, if you have 15% missing data, you just weigh the other distribution by 85%.
True, you could do that too.
Because now we have a distribution over how we weigh them, because that's the p split.
Yeah, good point. All right, moving on though.
Sorry,
No. I love your sidetracking. Don't get me wrong. I really love this because it jogs my brain as well. Moving on to practice M1. Using the mathematical form of the imputation model in the chapter, explain what is being assumed about how the missing values are generated. I just copied over the mathematical formulation from the book here because one might not remember that when looking at the solution on the website. And basically, when we look at this, the missing values lie in B. So this line right here, third line from the top, BI something something. This is the one we want to focus on. Now the assumption right here for our predictor for which we have missing values. So variable B has some missing values. What is the mathematical assumption in this model? The mathematical assumption here is just that this is simply completely random. We make some assumption about the distribution of the data in B, but we don't make any statement about what leads them to be missing. So we don't make any statement about what causes them to be missing. What we're looking at here right now is basically missing completely at random. Does that make sense?
Yeah.
Serena, you look confused there for a second. Does that make sense to you as well? Okay, cool. Moving on then. Practice M2. This is where we finally get into R code. And let me tell you, compiling this exercise document here for the website was a pain, because apparently when you run too many Stan models through R Markdown, it all gets assigned to the same model while it's being compiled. And Stan doesn't like having models be assigned to the same kind of output file. And then it just kept crashing on me. And it was such a hassle. And even the internet wasn't very helpful for it. So this was just not a good time. It took me about 2 hours to compile this piece of garbage and about 10 attempts. Solving this took a bit longer, don't get me wrong, but compiling this was a pain. So if you ever want to do anything with Stan models and R Markdown, it can get bothersome if you ever encounter a C stack trace error. That just tells you doing too many Stan models from R Markdown, at least from what I understood. But moving on, finally we're in R. So question for M2 was that in earlier chapters, we threw away cases from the primate milk data, so we could use the neocortex variable. That was incomplete case deletion. Now repeat the WAIC comparison example from chapter 6, but use imputation of the neocortex variable so you can include yada, 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 yada. Simplest form of the imputation model is acceptable, again, and so on. How are the model comparisons results affected? By being able to include all of the cases. Unfortunately, the model comparison example that Richard is after, I could not find any of that in chapter 6, but I found something that I think he was after in chapter 5. So I just ran with that one. And basically what I do is I load the data in. I'll also just make this a tiny bit bigger. I load the data in. I make my percentage into full-on bound between 0 and 1 rather than between 0 and 100. I then compute the log mass. I standardize the log mass as well as the energy content of the milk. But what I don't do, which is what the book does, is I don't standardize my neocortex variable. Because I thought, I know that the neocortex has to be between 0 and 1 because it's a percentage or proportion. And once I were to standardize it, I would have a much harder time setting a proper prior for this.
You can set up like in Stan, right? You have two, like in Stan, this is easy because there you have two fields. You have like a transform parameter and a parameter, right? And it's arbitrary whether you set the prior on the transform parameter or the parameter, right? As long as one of them has a prior, you're good.
I don't know how that works in Stan, to be honest, because I haven't done Stan code itself yet. I just know that there's different fields for priors and transformed priors.
Yeah.
But if that's possible, then fuck yes. Amazing.
Yeah, that's one thing that's really nice. Like, so Stan is more expressive, and that's the good and the bad part of it.
Yeah. All right, cool. Learned something new again today. So you may now ask, why did I say that? Just said it. Why did I not standardize? Again, just so I have an informative prior here that I can actually make use of. With all of that ready, I just run the models from chapter 5 when we still ran QAP. So I now make these into ULAM models.
I think you can do the same in ULAM. I'm not an R person, right? But if you just imagine you take the unstandardized one, you set a prior, and then you basically say, you know, variable name underscore standardized equals, and then you standardize that thing. And then that's what you use in the linear model. So then you're using the standardized one in the linear model because you have one extra line, just like when you're non-centering, right? You're just transforming it.
Yeah, so we would need to have a standardizing function on the prior that I'm setting, right?
No, like first you write the prior on the scale of the data that you like, right? And then you take that thing, whatever that is, and then you standardize it. And then you put that into the
now I get
model.
it. Now I get it. Yeah. I don't know if ULAM could execute that because that would assume that Stan knows how to standardize.
Yeah. Yes, I'm not like like I know at least in I'm using PyMC3, and there it's really easy because it's like Python code, so you don't have this distribution thing. Everything is an equal sign, and therefore everything is an assignment until you get to the likelihood. So as long as you have like an assignment of the prior and like a transformation of the prior in the next line, then you can use that transformation in the model.
All right.
Where this is like ULAM is more magical because you can have stuff in the wrong order, right? Like Richard is writing all the models upside down. And like you can't write, you have to write them like prior to likelihood in PyMC3 because it's Python, so it evaluates this line, it evaluates this line, so it cannot evaluate this line without knowing the prior, which it depends on, right? So there, because it flows that way, you can just have like a transformation in the middle of your model and everything is fine.
Yeah. All right, this is definitely worth looking into then, if you can do that here as well. But for now, I just ran with this. I took the models from chapter 5 and I just made them into imputation models, basically. The first model right here is just the effective mass on milk. So right here, we don't actually do any imputation. Second model is neocortex effect by itself, which in this case, I simply just took, so for each computation here, I just took 0.67, which is the average neocortex percentage, off of my value for P, the neocortex percentage, so that the intercept would now represent K, so the milk milk energy content for the average neocortex percentage. I could have also just completely skipped that, but I just wanted to see what happens. So then I have my beta distribution here for my p-values. It's a beta distribution because bound between 0 and 1. Same for the mean of that distribution, which I get right here for d beta 2. Everything else stays the same as previously, except for, so everything stays the same as in the models, as in chapter 5, except for one thing, and that is my prior for BP, the coefficient for the effect of neocortex percentage onto milk content, where I now have a much wider prior because there's a lot less variation in my p-values. Does that make sense? Because all of these are clumped a lot closer together because they're all somewhere around the range of 60 to 80%. If we standardize them, there's much more numerical range between them. And now, because there's less numerical range between them, I just put a wider prior because I legitimately don't know what's happening here. So I just don't want to influence the model too much.
But shouldn't it be the other way around? Like if the unstandardized scale is smaller than the standardized scale, the unstandardized prior should be smaller than the standardized one.
I disagree, but I don't know why I disagree. Let me think about that.
Like I think the reason you disagree is you can reason about the prior on one of the scales and not on the other scales. So it's more like it's because we're bad Bayesians, right? Because like it's like our prior should be scale invariant. But since we're human beings, they're not scale invariant. Right? My prior on height in foot is not the same as my prior on height in meter. If I had like very few seconds to think about it. And therefore, on one of the scales, I'm gonna use less of my prior knowledge than on the other scale. And I'm thinking that's what you're doing here.
Pretty much, yeah. Yeah, I could also see the case to be made for these should be tinier. It's
two different intuitions, right? In the standardized one, it's like, well, I know effect sizes are usually less than 2, right? So that's your standardized prior, right? And now you're not in standardized and you're like, crap, what is the effect of having 1% more brain? And you're like, I literally have no idea because I don't know how much like that.
Yeah,
but in that case, that's an argument for
pretty much where I was
standardizing.
coming from.
If you actually have a better intuition for what the price should be in the standardized land.
Yeah, but I don't. It's fun, isn't it? So then I only end this model with this vector 12. There's a 12 in here because there are 12 NA values in our data set, which we need to impute some p-values for from a uniform distribution between 0 and 1. Because I know neocortex percentage can't be below 0 and it can't be above 1. It's also probably never going to be 0 or 1, so I might have wanted to use a beta distribution for this instead of a uniform one to center it more towards the middle of the range, but I just went with uniform because I was done.
Yeah, so the reason this is not that bad, right? That's because you learn this latent distribution from the rest of the data, right? Because otherwise it's obviously super scary that like none of them has below of like the number 0.6 and above the number 0.8 or whatever the numbers are. And your prior is like, it has like only 20% of the mass in that area.
Yes, I could have constrained this prior way close to be way closer to the actual data that I have. But then I also, like, priors are not supposed to fit the data.
It's called empiric base, but I take your point.
Yeah. I mean, there are probably very clever people who would now beat me above the head for saying don't do that. But there are probably also very clever people who would beat the other people over the head for beating me over the head. So I guess this is just a vicious cycle of violence.
Like, philosophically, you're correct, right? I think where people can get away with it is like when they're doing a fake hierarchical model, right? Sometimes like you have some data and you know that it follows like some over distribution, and you can like, so like let's say you have like the classical one, you have baseball players, right? And they have some batting average, right? And the guy with the best batting average in the data set is the guy from the little league who hit it 3 times in a row, and that's all. Then he's done, right? He's better than the best guy in the world, right? And then you like fit some over distribution, and it's like over all of the data, it seems like it follows like a beta, some large number, right? And then if you, of course, put that beta over the guy who hit 3 out of 3, right? Then it's like suddenly like 53-50 in the posterior, right? And now he sucks.
Yeah.
And there you kind of also double dipped in the data, right? Because you just fit like the thing that should be a hierarchical model, you just fit that one like as a one step in like all of the data, and then you use that one for all of the data subsequently, right? But since there's like 1,000 people in your data set, like fitting a true parameter distribution is not like the end of the world.
Yeah.
And like here, like you could argue here you have only 12 missing values. So in a sense, like there is a lot of overfitting going on if you actually do this cheating trick. Well, I'm guessing, well, you're fitting them from all the ones that are not missing, and that's like 100. So there it's like you're almost not cheating.
Yeah.
But it is.
Yeah.
I agree. Like there's no defense apart from the pragmatic. It's almost not cheating, and it helps a lot.
True. I think this is where one really, again, from a philosophical standpoint, wades into some hot waters with what priors should actually tell us. Because I mean, if anyone scrutinizes a Bayesian model, the first thing they point to is always the priors.
Yeah. But I also think I think philosophically, right, when you do a real hierarchical model where you're not cheating, that's much more computationally expensive than doing the two-step trick. Like just doing like methods of moments as like a first hack for the adaptive prior is like surprisingly good. And then just using that, if it's conjugate to all the underlying data, it's like insanely fast, right? So you can like blazingly fast be an empirical Bayesian, and you can be like glacially slow be a real Bayesian. And like in the cases where they practically give the same result, it's very tempting to be an empirical Bayesian.
Yes, I fully agree with that. I mean, that's the whole idea behind frequentism.
Yeah, well, that's even worse, right?
Yeah. Fully agree. Let's move on. So this is where we run the second of these 3 models. This is the first imputation model. Now we just repeat the exact same model code, but now we fuse that with our priors for the BM parameter from the above model. So now we've got 2 individual models and 1 full model, 2 of which are actual imputation models. Because for one of the individual models, we didn't need to impute anything. So when we then compare all of these 3 models with the compare function, this is also why I ran everything with log-lig equals true, we see that, unsurprisingly, the full model outperforms both of the one-effect models here. The mass-only model still pulls ahead of the neocortex imputation model, but we would like to use our full model anyways. That's all that I'm after here. And that's all that the question really asked of me, to be honest.
So did you, in the ones where you don't impute, do you drop the data points, right?
Yes.
It's like,
so right here, the data points are automatically dropped, and all I needed to do to achieve that was just to remove the P slot from the data list.
Yeah, it is crazy to me that, and maybe it's just me who doesn't understand something, that you can actually compare the back of 2 models that are technically on different data. Because obviously, if your data set was twice as large, your information number would be like very different. So it seems like even like, let's say you actually messed up when you did this missing value stuff, like you're like totally cheating. You might risk still looking better because you have more data.
Yes and no, because I mean, you can still catch that information if you look at the PWAIC value, right?
What is the p-VAC? That's the number of effective parameters, right?
Yeah, which is influenced by our sample size.
No, it's not.
Is it not?
No. p-VAC is like, it's like when you have the hierarchical model and you have the not hierarchical model. If you have like this, if you have like 8 groups here, and you don't have the hierarchical model, then you and you have like a total flat prior, then that number will be 8. If you have like a prior that says it has to be positive,
oh shit, number, yeah, you're right.
It's gonna be 4.
You're right.
If you have a hierarchical model, so it's like how much it's the pooling that reduces the effective number of parameters. So this is something totally different.
No, you're absolutely spot on. Yeah.
So like my interest is, like, so what I'm afraid of is basically, let's say you took your model and you did like basically a prior predicted check, and you said what is the back of that, right? And then like obviously if you have twice as many prior samples, you're gonna get a better back, assuming your prior is better than random, right? It's like if there's excellent information in your prior, it's gonna be better than just like whatever the uniform null distribution magic is, the one that has like 0 VAC. And since like just having more prior stuff is basically what you have when you have missing values, it seems like you'll always sneak in. Like it might be it might just be that, well, oh, there's information in the prior, so it is better. But it just seems like you're comparing apples and oranges.
Yes, and I think other functions in R always safeguard against that. When you try to compute AIC and BIC for different models, it always checks if it's been run on the same data set. This one just doesn't.
No,
and I guess this is...
unless it has been run on the same data set. It's just like it's part of the model to drop some of the data. Right?
Yeah, I mean, it has been run on the same data set, but data points have been... No, wait, no, sorry. These are all run on the exact same data set because, sorry, yes, I got that wrong earlier when I answered your question. This model right here dropped diddly squat because this model didn't need to drop anything because there are no NAs in mass and milk content.
Yes. Yeah, okay, perfect.
Totally on me. Yeah, no, this didn't drop anything.
Yeah, then there's no cheating.
Yeah,
as long as the length of the output vector is the same, then it's
yes,
good.
it would have dropped stuff if I hadn't removed the P slot from the data list.
Yeah.
There we go. Solved that one. Then just for shits and giggles, I just repeat the plots from the book, which just show my imputed values against the observed values, as well as the uncertainty bands around them from my P imputation. So this is the vector of 12 values that get imputed just against log body mass and milk energy content.
Those are some very broad priors. There's some very broad distributions, right? They're like they
yes,
cut outside of the most extreme points. Like how many points are there?
Sorry, how many points are where?
There's 20 points, right? So basically you would expect one of them to be 2 standard deviation away, like in Dodgy math, right? Because like it's 1 out of 20. So you would expect the highest and the lowest to touch the uncertainty, like the ends of the uncertainty band on the imputed values, and they're not, right? So you have way too much error, like you're way too uncertain about your imputation compared to what I would assume you would see.
Sorry, I don't quite follow what you mean with touch certain things.
So like I would assume that like if you actually learned, like if you learned the distribution of these points from the data, I would like since the spread of the data is much less than the spread of this imputed point, I would assume that like if you just take like all of those points and plot the uncertainties on those points, that's less than the uncertainty on one of the imputed points, and that seems weird.
Right. I'm not sure I follow still. I'll try to rephrase it and you tell me if I understood correctly. So what I get right now is you would expect there to be more range on the y-axis. Let's just look at the right-hand side plot. You would expect there to be a bigger range in blue dots, which are the actual observed values, than you would expect individual error bars.
I would expect the difference between the largest and the smallest blue value to be about the size of the error bar. Since there's 20 points and a 95% confidence interval will have 19 out of 20 points.
Now I see what you mean. But I think the reason we see these very big error bars here is because it's
flat out the prior. There's no information.
Well,
like you're not learning it.
No. It's not flat out the prior. If it was flat out the prior, then these bars would extend all the way from 0.
Because it's uniform. Yeah. I remember. Yes. Yeah.
Yeah. So we definitely did learn something here. I would just like to point out that we don't have a lot of data points to begin with. And because there aren't that many data points, our model might be uncertain of where the regression line lies. And so there might be quite a number of sets of imputation points, which would still correspond to the regression line quite well. And that's why we get these super big error bars.
Yeah, like I'm not saying it's wrong. I'm just saying it doesn't like pass. Like my intuition would think something like drastically different, right? Like I would assume the errors would be half as wide.
Yes, and I see where that comes from. I fully agree with your intuition there. So my intuition agrees with yours. But I think the model just sees these data points and goes, well, this one could be up here, this one could be down here, and things would cancel each other out.
Yeah, right.
In terms of in terms of where the regression line lies.
Yeah, it's also like if the effect of new cortex, what so you have new cortex on one, and you have what is the thing on the other axis? The scroll,
Oh,
like
sorry, that's
body mass,
log
right?
body mass.
Yeah.
Standardized.
Right. So the thing is, like, if the, like you can see the regression line is really weak, right? Like if you plot, it's not like a line like this. It's like a line like this, right?
Mm-hmm.
And since you're predicting one from the other, right? That one could have very different numbers and still, yeah. So I take your point. It's like if the regression line were more steep, I think the errors would be smaller. It's because the regression line has so little information that you have very little information from the to flow from the outcome, which is where you have measured stuff, right? That's where your likelihood comes to flow back to the posterior of the missingness.
I agree 100%. Yeah. All right, moving on. Over to practice M3. Report the divorce measurement error models, but this time double the standard errors. Can you explain how doubling the standard errors impacts inference? So I just load the data, do everything they do in the model to it, standardizing and what have you.
It's the same as dividing the population by 4, right?
Sorry?
It's kind of the same as dividing the population by 4, right? Because the square root of 4 is 2.
Sorry. Oh, yes. 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 Sorry, I thought you were talking about the data manipulation and not about the model. That's why I was confused there for a second.
This is just my intuition to the effect of this fake intervention.
So
the intervention of like if you saved 75% of your budget, how would your model look?
Fair. So now I just run the baseline model, which has the normal standard deviation here, just to have this ready for comparison in a second. Now that we have that, we can run our...
Do we agree that like when you have wider standard errors on the mesh, then you would have more shrinkage, right?
Yes.
Because suddenly, like the trend line looks much more credible. Like if you're like here, then the trend line is wrong. If you're like here, then the trend line is good, and I was supposed to be down here, right?
Yeah, but stop, because I literally have shrinkage plots coming up.
And then are we dividing?
Yeah, go ahead.
Sorry. Are we dividing the standard errors with the standard deviation above?
Well, the standard error is the standard deviation divided by the population.
The DST.
Sorry, the DSD right here is the standard error divided by the standard deviation of the divorce. So is
that a way to calculate the standard?
No, this true, but this is how it was done in the book. I literally just copied that over. Yeah, I also would have probably just gone with SD of divorce here. But no, sorry. We have to get to a standard to a standard error for each individual state. And that's why we take the standard deviation across all states in terms of divorce rates and divide the individual measurement error for each state by that standard deviation across all divorces.
Yeah, this is basically you scaling it. Yeah.
Yeah.
Yeah. You have a distribution of things per state, and then
you're trying to explain the you're trying to explain the standard error of observed divorce rates per state, and try to make that comparable across all of our states by dividing by the standard deviation of all of the observed divorces, so that they're all comparable to one another. That makes sense?
Yeah.
Cool. All right. So now we simply run the exact same model as above, but we just multiply DSD by 2. I was very surprised when I figured out this was as simple as this exercise would be. When we then look at our model output, before getting into what has changed here, we can already see that the effective sample sizes are terrible for our second model, at least in comparison to our base model. And so without going into detail on that, I consulted the solutions by McElrath for this to get to a non-centered parameterization, and just copied over the non-centered parameterization model of this. So we have some more effective sampling. Luckily, he spotted this himself as well. Or luckily, I spotted what he had already spotted. So then I run the same model again, just now non-centered by addition of this line right here. So I get all of my prior dependencies just into my actual likelihood function. Like I said last time, all of the priors, just the likelihood function, and everything down from there is just numbers. But that's how we get to.
I am so confused. Like, why do you need to non-center it when it's not a hierarchical model?
So the reason it runs badly is because we now have made the posterior landscape difficult to identify, because we have increased the standard errors so much that it's difficult to find the valley.
Yeah,
that's like, basically what's happening here.
It's kind of yeah, because the DST was the one you already standardized. So you're so that okay. So you standardized that's the thing we debated it 2 minutes ago. I'm just an idiot.
Yes.
When we were confused.
You're not an idiot, but that's what we debated. Yes.
Yes. And of course, yeah. And so the whole model is set scored or scaled with regard to that. And now you're going to mess it up. So probably you should multiply by 2 somewhere else in the model, and you would not need to rescale, right? Can you scroll up to the one that is not standardized?
Yes.
And give me 5 seconds to think.
Totally.
And very soon. Yeah, okay. So, but you could basically just you could just do the old one and just have like d observed 2, and that should just be equal to d observed times 2, right? And then you would be fine.
No.
You wouldn't?
No, because then you would increase the value by a factor of 2.
You need to subtract the 2 first. Yeah. And that's basically the definition of non-centering. Yeah, sorry, my bad.
Yeah. No, all good. I'm just happy I could for once answer the question outright. Because that's just what's happening here.
Yeah. Perfect.
All right. Now when we run this, we see that our effective sample sizes are so much better. And now we can actually compare these models. It's also worth pointing out that this was just an exercise to get the NEEF higher, because these estimates right here are the exact same as for the non-centered, for the centered model.
And that's because 500 is a large number, right? So
yeah, like it is a large number.
500 samples, not bad, right? It's just better.
No, it's anything but bad, but also it's just not as good as that for the base model that we're trying to compare stuff to.
But like if you view it from the hidden Markov model perspective, not hidden Markov, but from the MCMC perspective, right? Then like if you had infinite samples, you would actually know the true bounds of these intervals, right? But since you don't have infinite samples, there's like a little bit of error from sampling on these bounds, right? And that sampling is based on 500 samples, right? So that's the square error of the sigma of the distribution divided by 500, right? Well, no, divided by the square root of 500. And in the other one, it's the square root of 2000, right? And since there's a factor of 4 between those, that's a factor of 2 in error, right? So you have your error coming from the MCMC, but it's still already really small, because it's the square root of 500 that is now twice as large.
It is also worth pointing out that we were just looking at the uppermost NEF value, and the sigma value.
The sigma one is messed up. Yeah, that's messed up.
That's just too low. We don't want that.
Yeah, I agree. I completely agree.
And it's looking so much better over here.
Yeah.
Now that we've got rid of the issue, the big thing to point out here is that the basically alpha has almost stayed the same, BA has almost stayed the same. Only really sigma and BM have changed. And the BM coefficient has increased, as a matter of fact. where now, what am I saying here? By increasing the standard error, you have effectively allowed individual states. So where divorce rate is super high, for example, and marriage rate is super high, to allow to inform the model much stronger than previously. Does that make sense? Because there's now a bigger error distribution. Our individual states are allowed to just lie away from the regression line a bit more, thus pulling the regression line in different directions, which leads to different parameter estimates.
Yes. So the divorce is the outcome variable. We're predicting divorce from the two other ones, right?
Exactly.
So the outcome variable now has a lot of residual error because like the sigma thing is way larger. And therefore, both of the things that are predictive of that one can now be pulled further in. But
yeah,
marriage is more predictive of divorce than age is, and that's why marriage is the one that is pulled in.
Sorry, no, age is more predictive of divorce than marriage is.
But why is age then unchanged?
I think age might remain relatively unchanged because there's not that much variation states level wise.
Yeah, or it's because my intuition sucks, right? And it's the other way around. That if it's actually predictive, you can reel it in. But if it's not predictive and suddenly it's explained by it's twice as likely to be noise, then you reel it in.
I think that's it. Yeah. All right. Just quickly go into transfers into the hard exercises. I'm going to go through them really quickly now, because we just crossed the 2-hour mark. Serena already had to leave us, and honestly, I can just feel myself going scatterbrained here. So let's just speed through them. The practice exercise H1, the data in data elephants, counts of matings for bull elephants in different ages. There's a strong positive relationship between age and matings, but age is not always assessed accurately. Basically, just fit a Poisson model between matings predicted through age, then assume that the age values have a standard error of ±5, so 5 years that is, and then re-estimate that relationship. When you incorporate the measurement error, compare the inferences in the two models. So I just load the data. I quickly look at the data, and then I build my first model. In this first model, there's one thing that is important to point out, and that is that I subtract the value of 25 from each individual age, because looking at the data set, the lowest age that is recorded is 27. So I assume that must be sometime around when elephants mature sexually. And just to be on the safe side, I thought probably they mature at around 25. And I wanted to get to an understanding of the effect of age past sexual maturity. So I want my value of 0 to be roughly around where elephants could potentially even start mating. So that's just what I do here. I run the base model, which just has the Poisson distribution with my log scale right here. This should all make sense, I think. And now, again, pointing out that this is a not so efficient sampling model, but whatever, just quickly see how does this model understand the relationship between age and matings. And for this, I just extract this relationship here, and this is how the baseline model sees our relationship between age and matings. The older you get, the more matings you have as an elephant bull. We could discuss whether this fits the data perfectly or not. It obviously doesn't, but also there's just a lot of spread in the data. So now we want to account for potential age mismeasurements. Now, to do that, I run the measurement error model. This is just where I do a bit of garbage collection so I can get it all to run. And I just should have put that in a different chunk, but whatever. This is just why I run garbage collection. Because otherwise I run into that multiple stand model error, and it's infuriating. And now I'm not going to recompile this webpage because I'm so done with this. No, I just need to vent about my frustration because I was pissed yesterday when this just wouldn't compile. So now I just save my age of 0 directly into my data set, where I just subtract 25 as the age of sexual maturity, so I can save myself some typing in the measurement error model. For my measurement error model, I now have my estimated age, which is the true age that I want to estimate through my model. This is basically just the mean of a normal distribution from my observed age, age 0, with a error around it of 5 years, plus minus 5 years, which is what the question asked of me. And now when I run this model,
assuming you interpret plus minus 5 as sigma equals 5 and not as like the 95% interval equals 5, which would be 2.5, right? It's very loose what that plus minus 5 means. Right. So point taken.
I could have definitely done some more stuff to this to get it to exactly within 5 years, everything must be there.
Yeah.
But luckily, if I had done that, not much would have changed here. The shrinkage plots that I'm about to show would have changed a bit, but the overall take-home message here wouldn't have changed. And the big take-home message is that our BA estimate has not changed between the two models. With the measurement error model below and the non-measurement error model above, they are both around 0.7.
Yeah, but like you can actually have negative ages now, right, in your model, because you're subtracting 27. So you have an elephant that is 2 years old plus minus 5.
Yes, we could. We don't end up with this for a really cool reason in a second, but we could. You're right. So basically, why we don't see a change here in BAs comes down to us having assumed that the error is completely symmetric. So it can either lie, we could have either measured to below what they're actually old or above to what they're actually old. And we have also assumed that the measurement error is completely the same across all of our potential age ranges, which is not true with nature. It might be much easier to judge the age of a young elephant than it would be to judge the age of an old elephant.
I'm still not fully following. Like if Johnny has had 0 sexual partners and he's 1 year old, he's 26 years, he's 28 years old or whatever. It's just that he's 1 year old in your math, right?
Yeah.
Then like if you had 10 partners, like the model would actually assume he's probably older. That's how why he has had 10 partners, right? So when he has had 0 partners, then the model should assume he's somewhat younger. So even if he's 1 year old, and
this is exactly what I'm showing here. That is exactly what this plot right here is showing. Because you can see everything where the observed value, blue dot, falls above the regression line. This falls apart down here. That's just because this regression line is drawn with just a few points. That's why this is falling apart there. And if we drew more points, this would fit much better. You know what I'm talking about. What you can see here is that if the point falls above the regression line, so you have more sexual partners than the model expects for your given age, the shrinkage goes to the right and it says measurement error was probably such that we thought they were younger than they actually are.
Yeah.
And if you have less partners than would be expected from the regression line at your age, then the model says probably younger than we thought they were.
Yeah. Yeah. So what was wrong in my logic was you can't be dragged across. Yeah, you can actually be dragged across the line.
Sorry, no, you can't. This is only because the line is very rough.
Okay. There's very few points. Yeah. Okay.
Yes, the line is extremely coarse, and I should have drawn this finer to make this clearer. But again, I'm not recompiling this shit.
No. It's like it makes sense.
No, all good. No. I fully agree though. From this picture alone, your intuition is completely right. It's just that the picture is slightly off.
Yeah, and my intuition was wrong in the sense that obviously it's called shrinkage because you shrink towards the mean. You can't shrink past the mean, and that's why you're safe. You don't get negative old elephants as I a priori would have assumed because it's hard to fully connect how the data flows through the model.
Yes, so let's just say if you are 1 year old and have 0 partners, because that's kind of expected for 1 year olds.
Yeah, but it's not fully. It's expected you to have like 5% of a partner, right? So you'll still be pulled like so you're probably one month younger, right?
Yeah. but it's not pulling you below 0.
Yeah,
basically.
exactly.
Yeah. Also, for this plotting, I just added the 25 back onto it, just to have it be on the proper scales again.
Yeah. But like if you had somebody that moved to age 24, like I would have proven my point, right? And you don't.
Mm-hmm. All right. Practice H2. Repeat the model fitting problem from above. Now increase the assumed standard error on age. How large does the standard error have to get before the posterior mean for the coefficient on age reaches 0? Basically, this is trial and error. Run this model several times. Just increase this standard error right here in our adaptive prior until our BA just falls to 0. And I kept increasing it. I finally just landed on 100, and that's where I stopped, because I didn't feel like running the model again and again and again and again. I could have probably written a for loop that tests for this and then just spits out the right number, but that would just take way too long. So I just trial and error dialed this in on roughly 100. Our BA value has shrunk, but it's not completely 0 yet. However, I argue that the interval is so wide that we could not credibly say, oh, it's exactly 0.3. And that's just where I stop.
It's also ridiculous having like an error on like 100 years.
Right? Makes no sense. All right, moving on to the second to last exercise, practice H3. The fact that information flows in all directions among parameters sometimes leads to rather...
What would have happened if you did a uniform distribution on age instead of having done a normal one? I think then you would have messed it up straight away.
Yes, you could have messed that up much, much harder.
Yeah, sorry, continue.
No, but true, absolutely right. Practice H3. The fact that information flows in all directions among parameters sometimes leads to rather unintuitive conclusions. Here's an example from missing data imputation, in which imputation of a single datum reverses the direction of an inferred relationship. Use the data. This is the data right here. And this is the model we are supposed to run. Interestingly enough, you can also call the persist function on LM objects in R, which I think is quite cool. But the important thing here to point out is that without going into how I ran the models, how we end up with a bimodal posterior distribution, it's just if we think about the underlying data here, why might imputation go completely wrong? And that's because if we look at the actual range of data values, all of our Y values fall somewhere around 10. And all of our X values also fall somewhere around 10. However, the one value which we have to impute for X has a Y value of 100, which means it's really far away from all of the other data points, hence why imputation really struggles. And the reason it struggles is because if we run this entire thing and then just plot the potential outcomes of the imputation, we could either have the imputation assume that we have a super extreme X value on the positive side of things, and we would still have our nice regression line that is completely compatible with the actual data down here to the left. Or we could have our data point flip to the other side and everything could be fine and dandy with the data that we have. Because all of this still fits the regression line just the same way and just as fine as it does in the left-hand plot. And that's the danger, at least that's the takeaway for me with this imputation. The danger with imputation is imputing variables that are really far away from imputing variable values that are really far away from all of the other variable values. So you would probably want to use imputation mostly for missing data points where all of the other variables fall into a good cloud of data points and values. Does that make sense? I think Jan is currently busy.
It makes sense. No, whenever my wife walks by, I'm just turning on the camera to be nice. So it makes sense, but like sometimes, like if all the small monkeys has not, like you haven't measured something on them, then it falls. Like, and if there's more large monkeys than small monkeys, then there's like it's just game over, right? Because like you have missing data in a small subset of your data, so you have to.
It's basically a systematic bias.
Yeah.
Yeah. Only in this case, it's hard to call this a systematic bias because there's only one data point that's missing, and that one just happens to be the extreme one.
Yeah. But like usually it is the extreme data points that are missing, right?
Yeah. All right, last example, and I will speed through this quite a bit because I had to copy a lot of the solution here. And I think it's best if we all take some time and try to understand this and then talk about this in the summary meeting when we bring up some issues, because I have issues with this one. And this is mostly the stand code that is going to be introduced here soon, because we just haven't learned how to write stand code in this course yet. So someone called Andrew had an 8-sided spinner, spun it several times, recorded how often each side came up, but then spilled some coffee on his notes. And unfortunately, now he doesn't know how often the sides 4 and 5 came up. And he wants to understand if the spinner could be considered fair or not. So we need to impute the number of sides with which 4 and 5 probably have come up. So we just enter the data, and now there's a couple of things we don't know. First of all is how many total spins are there? Well, we don't know how many total spins were there because we don't know how often 4 and 5 were observed. So we don't know how many spins were behind that. But what we do know is how often everything else was observed. So everything except the NAs. And if we sum all of these results up, we get 120. So we know that there have at least been 120 total spins. I suggest that we probably had around 40 spins for 4 and 5 so combined, because that's how often everything else was spun, roughly everything else was spun 20 times. And that's just my intuition going. Good prior here would probably be to say Poisson distributed expected value is 40 plus 120 outside of the Poisson distribution, because we know that there were at least 120 spins.
I think if it's on 40 is too narrow, right? I would assume, because then you have this pretty heavy prior that it's a fair spinner, right? I know very little about spinners, but if it was like a spinner like that came out from like a funny gadget shop, or a spinner that came out of like Walmart, then you have different priors on like what would you expect to happen here, right? And
yes.
since you should encompass both of them in your hypothesis space, I would like a distribution that can that has the propensity for over dispersion.
Fair enough. Yes, it might be valid to use a quasi Poisson here instead of a Poisson. Good point.
Because otherwise, like you can a priori just say you're going to come to the conclusion that it's a fair one now, because it's centered on the values that the other ones have.
Yeah. Next thing we don't know about this is the.
Well, if anything, you should use the variance between the other numbers to actually get a feel for what the dispersion should be.
That would be a good call too, unless this just so happens to be a spinner which never shows 4 or 5.
I totally take that point, but at least that will give you some intuition about whether it's a regular process, right? Because if you see the number 1, 2, 3, and then 43, 44, 45, then you would not have guessed, well, it seems like the middle value is 40, so I'm just going to stuff in 40. You say, well, it looks like it's over dispersed.
Yeah. No, I fully agree with you. Let's move on to the probabilities for each side coming up. We don't know that because we don't know the total number of spins. So we can't get to that from our data. But what the exercise did tell us was to use a Dirichlet prior, which is used for categorical outcomes, and that no outcome is more than twice as likely as any other outcome. And we can just test that. So I just run a Dirichlet here for, I simulate 1,000 random numbers from the R Dirichlet distribution. And I just put 4 as my alpha. This is just the shape parameter, and repeat that 8 times because we have 8 categories. Then I plot that bad boy, and I've got absolutely no idea if any one of these is more than 4 times as likely as another. There's probably a good chance that this is 4 times, that this is at least 2 times as likely as this one.
Yeah.
But honestly, let's just write a function for this. This function just extracts all of the different numbers and checks if any category is more than twice as likely than any other, and then just returns the number of how often that is the case in our prior. In this case right here with the prior we just ran, out of 1,000 samples for 977 of the resulting Dirichlet distributions, this is violated. This assumption or constraint is violated, so bad prior. Let's make another more constrained prior where I just up alpha to 50. This was just playing around to get to something. And now out of 1,000, only 15 violate that constraint. Honestly, I'm fine with that. 15 out of 1,000. Yeah, the model should correct that for us. So this is the prior that we end up with, the Dirichlet prior. So now we don't know the counts of spins that resulted in 4 and spins that resulted in 5, and that's exactly what we want. We want to know the most probable combination of these two numbers, given everything that we outlined so far. And this is where then McElreath builds a full-on just Stan model by itself, which I try to understand and add some comments to know what each line is doing. But I'm still a bit hesitant on saying I understand this because I don't. I just run this, then just look at what the posterior produces. And right here, we can see that, yeah, the combination of 20 and 20 spins for 4s and 5s is totally the most probable. Who would have guessed? But the way we get there was just a bit complicated. And Jan, it sounds like you have a bit of Stan experience.
I have no. I've never written a Stan program. I've just read the code in our Stan level is on par, I think. I've done a lot of times C3, which is closer to Stan than ULAM is, because it's like Stan. Yeah, but it's I haven't done Stan. Like I would like to do it. Like so, eventually I'm going to do it just to learn it in some projects.
So in that case, I would just suggest instead of us trying to rack our brains and understand this right now, we just call it quits here, but we use it as, let's say homework, even though I hate that word, for in 2 weeks, we just try to walk through this again in 2 weeks when we have a bit of a clearer mind and more people present. That sound good to everyone?
Yeah.
Coolio. In that case, we are actually done for the day. That was good. That was another good session.
Yeah.
That definitely made a lot of things a lot clearer for me.
Yeah. And then in 2 weeks, we're calling it quits, or are we just gonna meet like once a month with fun stuff, or what are you thinking? Because like you have spent so much time, Eric. So if I was you, I would not commit to anything that required anything of me.
Yeah, no, and I definitely wouldn't. I am more than happy to, I actually love the suggestion to just do fun things every now and then, like a monthly meeting. I love that idea a lot. But I think with the monthly meetings, we would have to structure it as we just have a Google Doc or something and people just sign up for, I read a cool paper, let me just show that to people. Yeah.
Yeah, like one thing I could suggest was the Stan. There's like a Stan case study webpage, which basically has like the SIA model. So you and like some of these advanced models, and we could just pick a Stan case study and just go through it together. Like it's not
like that.
Like we just read it and then whatever. Like I'm like why is an integral here? And then hopefully somebody knows, right? Just like it's not on anybody to make slides or anything. Just scroll. Like somebody shares the web page where we can see it and we just scroll and talk.
Yeah, I like that. I think that would be really cool and useful to people, and also just nice to keep everyone working with Bayes. Yeah. No, that's a really nice suggestion. I will put that into the update email that I'm sending out as well. Also, there is going to be a session next week to deal with the last 2 chapters in the book, and then the week after that we've got a summary session.
Sounds good.
All right. Please don't forget to send me open questions.
I was supposed to send you 2 things. I forgot. Like something with all the books and something with what is the other thing?
The other thing was just questions that we should address in our summary in our summary thing. And I said that for some of the questions, I'm probably going to share the questions that I collect over the next few days and weeks, because I think that you are, and no offense to anyone else, both here present right now and watching the recording later, but I think it's fairly apparent that Jan is one of the more advanced Bayesians in our group. So it might be useful to get your input on the questions as well that come up.
Yeah, sounds good.
All right. Good stuff, people. I think that is it for us. All right. See you all next week.
Right, thank you.